Okay, so welcome back to the second half of your 11th class, where we go into unsupervised machine learning. This chapter, there are two big parts, okay? The part that I covered before the break was cluster analysis. The other part, dimensionality reduction, I haven't. I will go through that as we come. But first, I want to show you the coding for cluster analysis. Again, this is language reference guide. So there's a page called clustering analysis with a lot of example. You can go through that in your time. Okay. Now, I make a quick note. This is mode of cluster analysis. Again, I this thing called once and done. So basically, I would use this function called find clusters. Okay, this guy, right? So this basically just if I put the data in here. So basically, a data is a list, right? So what is going to happen? What's going to happen is the output of this clustering is to make it a list of lists. Okay, so if you separate into 3 clusters, then it will be open curly bracket, open curly bracket, the first cluster, close curly bracket, close, open curly bracket, second cluster. Okay, so it'll be list of lists. Okay, so nested curly bracket. Okay, so here, so for example, yeah, find cluster and you give it 1 curly bracket, you're gonna end up with a curly bracket of curly brackets. Okay, fine. So that's kind of like what I call once and done. And this would make sense if you haven't done any clustering. Okay, if you want to redo your clustering because you have a new data or new population added, and it's a sizable chunk compared to what you got, right? But if you want to learn the clustering and then use it for the foreseeable future, so that when you get a new sample, you basically make an assignment. This one belongs to cluster 1, 2, 3. So that's called learning the partition. You would use this thing called cluster classify. Okay, see that? So there is the word classified like we had before. So you end up with a classifier function. But instead of classifier function for the label you give it to, this will become arbitrary label 1, 2, 3. Okay. So this is called cluster classify. I'll show you how both work. Okay. So that's, okay. So let's look at the method. Now, roughly speaking, I mentioned to you this kind of distance-based and density-based. There's this thing also called hierarchical clustering. This is also very useful, but I didn't cover that, but you can read that. It's called cluster tree, dendrogram. This is a lot more interesting in that it gives you some sort of like, you guys seen like taxonomy, phylogenetic tree, like separate into mammals and mammals into primates and primates into big ape, small ape, that sort of thing. We'll see example, okay? It makes sense to you. But anyway, so these are all the popular method. You can read through them. Now the density cluster, I kind of made a little example. You don't have to key in this. This is a bit too long to program. Again, imagine that you see this light at night. These are the dots. These are the dots, right? If nobody told you, you would still see that there's kind of like an S shape and 2 of them. Well, the reveal is that the reason you get 2 villages separated like this is because there's a river in between, okay? So this red and blue here, East Bank Village, West Bank Village, if this were a classification problem, that will be the label, predefined label. But imagine that this is not predefined label. You take a satellite picture at night, you just see a bunch of house with lights, right? And then you can say, you know, it looks like 2S, but it doesn't look like one lump, okay? This is the reason why. Anyway, so the popular one is called DB scan. It's short for density based. There's a word density right there. Density based spatial clustering application. So it's kind of like Gaussian mixture. These are all interesting. And this one is a hybrid, nearest neighbor kind of thing. I haven't gone through in depth. So this would be something that's quite interesting if you go into a machine learning class. Anyway, so let's demonstrate. Okay, let's demonstrate. Now, This one, just to show you completely, I'm making random number, okay? Instead of random number, I'm going to make a random hue. So these are all the colors. These are all the colors, right? Imagine, I don't know if you were kids, you had this pencil case, like color pencil, right? And you take out the box and then you take them all out and they have to rearrange it back. Somehow you have to kind of arrange from yellow to green to blue to red to, you know, that sort of thing. Well, it's kind of like that. So this is my random color. I call random hue 100, okay? I can get another one. Let's be another in the random number, but I see the random, so it always come out the same. So now I use what's called cluster tree. So I use this to demonstrate the cluster hierarchical. So let's do cluster tree. And, there it is. See, this is very nice. In most applications, you don't use this hierarchical clustering. Why? Well, think about it. If you use if your interest is to cluster your client into groups, sometimes you just have to assign, like, you know, one cell representative to cluster 1, 2, 3. You don't have to have this kind of family tree, okay? But in some problem you might, but this is computationally fairly, I think, more intensive. Okay, so this is called clustering tree. The other one is called dendrogram. Dendrogram is also very nice. See, it has this kind of thing. Again, you can imagine the bottom is like arranging colors. Okay, kind of arranging your pencil, color pencil in shades. Okay, so this is trying, the computer is trying its best to sort of like make this gradation. Okay, and so you would imagine that. Now, what's cool about this hierarchical is this. You guys remember that example? I say you separate your client to 3 groups, right? That's 3, right? But what if you kind of like want to have a whole picture of how your clients are partitioned? So these are all my clients. You can say that, okay, there's a kind of niche group and there's a large group, and this large group separate into 2 large groups. You see what I mean? Yeah. So maybe you have a niche person do this kind of client, and then you have 3 people for this large group of client, and 2 more for this, you know. So it's kind of like more flexible. It's not like a fixed flat number 3. So this gives you a sort of way of organizing hierarchy. So likewise here, you can say maybe this is one client group. Here this one, here's another. Maybe you put 2 here, you know, whatever. But you get the point, right? Now this is where we do the fine cluster one. So this would be like cluster 1, 2, 3, 4. This is the flat clustering. Whereas cluster classify, now this is different. Cluster classify means you are learning the partition like this. So become something, say, 6 groups, okay? And then you do something like this. Okay, this is 1, 2, 3, 4. So this is just kind of random assignment. Okay. So do follow this reasoning, and key, maybe as part of your homework, just replicate the codes here. You will see that what I did was to say, okay, these are the cluster, right? But instead of doing it once, I make it into some kind of classifier. 1, 2, 3, 4, 5, 6 types. Okay, that's it, I think. Okay. So anyway, that's kind of like, so now the reason we did it this way is if I have a new sample, I haven't seen this guy before, I would say, oh, this is this one belongs to cluster 2, this one belongs to cluster 6. So this one would go to cluster 2, this one would go to cluster 6. Okay, right. Again, the number is arbitrary. If this were a real client classification, clustering assignment I do for my consultancy, right? I would actually go look at this and say, hey, I'm going to call this first cluster, instead of just 1, I'm going to call this earth tone group, right? This one, I'm not going to call it cluster number 2. I'm going to call it light green, something like that, right? Maybe the last group I'll call. The point is that the clustering is done by the data. I don't come in with the preconception that, yeah, there's going to be a red group, a blue group, a green group. Okay. In fact, if you look at this, there's not that much red. There's only a little bit here. I'll call this fiery group, maybe, whatever. Okay. So you can see why this kind of market, if you pick up marketing book 101, right? They're going to talk about market segmentation, right? But you can see how preconceived they are. They would say something like, well, we look at the age profile and we separate into young adult, old age, retiree. So those are preconceived. And more important than that, not only is it preconceived, it is one-dimensional, right? So you separate by age, that's one dimension. You separate by wealth, maybe that's another dimension. But when you do this kind of multi-dimensional clustering, you may end up with a young rich versus old rich. You see what I mean, right? So it's more natural, it's more responsive to what is out there. And this actually I struggle with in my professional life, because a lot of people that I did the analysis for, they came from traditional marketing. So they have this preconceived notion of, this is my segment 1, segment 2. Sometimes it makes sense, like, you know, retail banking and wholesale banking. You really have to separate that because it's managed differently. But if you're going to do finer segment like Visa card behavior, you can't come up with a preconceived notion. And you can't say, these are my 3 types and there are 1 million each. No, it's not going to be. Look at this. There's only 3 of this, but there's a whole bunch more of that, for example. Okay. So if this were my client, maybe I would have 1, 2, 3, 4, 5, 6 segments. But this segment and that segment can be handled by 1 sales representative. This segment alone, I would have 2 sales representatives, 3 sales representatives, right? Nothing preconceived. The data tells me what to do. Okay, that's the philosophy we want. Okay. Okay, now this is interesting. You guys remember the Old Faithful data, right? 2 dimension, yeah. Now, if you will recall, it kind of has that nice kind of like ellipsoid shape. I bet you, I haven't done it. Actually, maybe I should. Okay, just I didn't think about it. I should fit a Gaussian mixture, right? So maybe there's a Gaussian for the small cavity, wait for about 40 minutes. The water spout shoot for 2 minutes. And there's a larger cavity, right? Waits for about 80 minutes, but then it shoots for 40 minutes, 4 minutes. Okay. So maybe I could actually fit a Gaussian mixture, right? But I didn't. Anyway, the point is, if you are going to do this kind of clustering analysis here, okay, so load the data. Yeah, see. Now, you guys remember the picture that we had before, where I have 2 data. One of them has blue and red. The other one has same color, brown. Exact same thing I'm trying to represent here. When we were doing the classification problem, we would have noticed that this is blue and orange, right? So maybe if I knew, let's say, if I knew, let's say geologists have a way of saying that is from the big cavity. So instead of having this data, this one will be red, this one will be blue. Okay. But I don't. This is unlabeled. Okay. So when I cluster the data, I'm going to say, okay, this is one group, this is another group. And if I learn the partition, then I can make an assignment. This is cluster 1, this is cluster 2. Then I can start to put colors, right? So the label comes after. It did not come with the data. I make the assignment and you'll see how, right? So there it is. So I find cluster. So this is, okay. So this would be how I found the cluster. By the way, this is a long story short. So that's kind of like k-means, but to centroid. See that centroid? So this one is the center of that. This one's the center of that. And for every green one, you will find that it's closer to the red dot than it is to the blue dot. So this is kind of distance-based clustering. Okay. So ask this guy, who are you closest to? You're closer to red than blue. Okay. But the way the algorithm starts is actually these 2 points that move. It's this blue and red point that moves. Okay, fine. Now this is where you learn the classifier, right? So again, two class. So now, so this is my twos, this is my ones. So basically these are these guys and these are that guys. So that's a partition. In fact, that's the ratio. If I were to do a mixture model, you would see that they're about twice as often in the twos as it is in the one. So maybe, yeah, that kind of makes sense. Why do you think that is? Well, I hypothesize, right, that we have small cavity and we have big cavities, right? Big cavity takes a longer time to fill, wait for about 80 minutes, but choose for 4 minutes. The shorter cavity, you wait about 40, 50 minutes, but it only chews for 20 minutes. And actually, there are about twice as many long cavity as short cavity. Well, maybe it's because the large cavity have a big input port. So it's more likely that water would drip into there. I don't know, okay? I'm not a geologist. I'm just making all this up, okay? But you can see why this gives you that kind of picture. Okay. So now once I learned the partition, I got new sample, guys. This sample shoot for 2 minutes and waited for 45. I think you know where I'm going with this. This is probably cluster number 1, right? And this one shoot for 44 minutes and wait for 89 minutes. So let's see if that works. Oops, I haven't built this. Oh. Oops. Sorry. Cluster classify all faithful. I think I named it wrong. My bad. There. So this guy belongs to cluster 1. So belong with these people. This guy belong to cluster 2, belong to these. So basically the big cavity as opposed to small cavity. Okay, so that's done. Okay. Now this is even more interesting. I make a data that's kind of like, I don't want to say you have to do this, but I strongly encourage you to actually key this in, because you will see that now I actually create a data that has this kind of thing, but I can actually move it so that it blurs. So it becomes a little bit harder to classify. So let's say what I do is I make a, so something like this. You can imagine that you can almost not distinguish between different cluster. But if you were to do this and maybe separate it all out, okay, then maybe you can see that there are 3 clusters. So this is what I use to generate sample so that you can test your algorithm, basically. Now, you guys are not in the business of creating a clustering algorithm, but you can imagine that you can create test case using this kind of thing, right? So here, you would hope that any kind of clustering algorithm you have will have three distinguishable cluster, right? It's very easy because it so far apart. Okay. But if I kind of move things close together, now there's only one lump. Any algorithm is going to tell you that there's only one lump, for example. Now, some cluster algorithm will give you the number of cluster. Some algorithm requires you to specify. K-means is one of those. K is the number of cluster. So when you use K-means algorithm, you have to tell it how many you want. So when you say K-means, you have to say K is equal to 3. That's what K means, okay? K-means in the K-means. Okay, so we can do that. Right, now. Okay, let's go with the real data. And this is where I really want you to, I will give you this data set if you want, but I think it's in the GitHub. Okay, so in the preamble or introduction book, a part of the book, there's a URL for the GitHub page for this book. You go there and you can download this data set, right? But if not, I can give it to you, whatever. Okay, so this is kind of like data COVID. The reason I make it a hard file is because Well, first of all, you can download from real life, which I did, but then you have to do this kind of formatting. And because COVID is no longer active, if you go to COVID today, it may be stale. I don't know. Okay. So I just froze it. And this is the day I froze it. It's the 22nd of February, 2022. Okay. So this is data from Ovid. Ovid COVID is ourworldindata.org. Okay, so I use that data from that day and I compile it. Anyway, now here's what I mean. So far, life has been easy for you guys, right? Because if I didn't use a computer, you can use your hand. You can use your hand because there's only 2 dimensions, right? For the old faithful, there's only 2 dimensions here. This is 2 dimensions. And so is this, right? Duration and waiting time, 2 dimensions, right? So you can circle this. In real life, you don't have 2 dimension data. In this COVID, what happened is these are statistics for countries. Also like region, like Southeast Asia or something like that, okay? Anyway, look, how many, okay, let's look at a heading with me. Number 1, location. So this is identification, basically Thailand, Indonesia, Malaysia, United States, China, okay? Now, these are the cases. Sorry, these are the statistics. Total case, total death, case per million, death per million, reproduction rate. This is not reproduction of human population, it's reproduction of the disease, okay? Basically contagion. Vaccination, people vaccinate, people fully vaccinate, vaccination per 100, people vaccinate per 100. So maybe total vaccination would count for like 3 vaccines if you've been applied. So 1 person can receive 3 doses, for example. People vaccinate per 100, total booster, stringency index. This is good. This is kind of like a qualitative scoring of how strict the government is. Population density, median age 65 and older, age 70 older, GDP per capita, extreme poverty, cardiovascular death rate, diabetes prevalence because it's related, female smoker, male smoker, hand washing facility, hospital beds, life expectancy, human development index. Actually, if you go to the Ovid or Our World in Data website, they have even more data field than that. Okay, so this data here that I put in my GitHub and use here has 28 attribute. Okay, the first one is location, so that's kind of an ID, right? So 241 location, mostly country, also continent. 28 attribute fields. Okay, so now we got from 2 attribute to 28 attribute. Can any of you draw a picture in 28 dimension? No, I don't think you can, right? So now even 28 is a little bit much. So I'm going to focus down to, I think, 10 or 12. So what I did was I did this and stats of interest. So basically, the way I did it was I list all that and I just basically comment out the one I'm not interested in, and then I pick the field. Okay, I'm going to describe it. You can look at it in detail. So basically, I look at the heading above, right? And then the one I don't like, I just block it out. I could have just erased it, but I use comment out, and I apply that to stat of interest. Okay, so now I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15 dimension, I think. Okay. Now, chances are these are statistical. I'm not going to go into the justification, but I think for this case, distance-based would probably work best. Okay. Now, what I did was, before, the reason I would do that, okay, first of all, well, let's check out. Let's look at all the statistics and do the histogram. Again, visualization is the beginning of everything. So I visualize that. So that's my case per million. By the way, I don't use number of cases because I want to do like a per capita basis, right? So I want to I want to cluster countries and location on Earth based on COVID and health data. That is sort of like per capita. So I have number like cases per millions. Minimum is 8 cases per million. Maximum is 100,000 cases per million. No, sorry, 600,000 cases per million. Wow, that's a lot, right? Yeah. Case per million, 600,000. That's like 2/3 of country. Oh yeah, that's possible. It's possible. There's some country that's like 2/3. For example, country in the Pacific Island. Sometimes it's very small country. They have like 2,000 people and 1,200 have COVID. So that's possible. Okay, so this is ratio basically. Death per million, 3 per million. Thailand is at the lower end, minimum, median, max. Reproduction rate, that's the rate of contagion. Vaccination, population density. So these are all the things that I'm interested in, okay? So I haven't done any clustering yet. So let's say I want to do cluster. I want three groups. So I do this. So I find the cluster. And now I apply to the cluster. Okay, so of all the 200 locations, there's 53 of the cluster 118, and let's say, okay. I'm going very quickly, so you can't key in everything here. That's okay. Okay. I'm sorry. I should have planned my time better in the previous class. I think before the break, I spent too much time on explanation. Maybe I should have gotten more on the looking back. Anyway, so now if you type in this in, it say, I find out mean applied to all the cluster, right? So in other words, cluster health stat, this separate all the location into 53 of cluster 1, 118 of cluster 2, and 70 of cluster 1, third cluster. And then I apply mean to each. So that's my means. Okay. Now, what do you think that means looks like? Okay, so these are just means. By the way, there is a normalization step somewhere. I should have, yeah. Clustering, if you notice, is not scale invariant. Okay. Yeah, let me go back to this picture. I forgot to explain this when I had the chalkboard. Okay. Now, you guys imagine this, yeah? Imagine this. You see these two clusters here? That makes sense, right? In other words, this dimension and that dimension kind of means the same impact here, right? Imagine, okay, if mean unit mating time is separate by tens, right? What if I go to duration and I separate by microsecond? In other words, from 1.5 to 2, it will be 1.5000001 second. What do you think that's going to happen? I'm going to stretch this axis, right? If I spread this axis so much, now this axis is going to matter more when it comes to the clustering, right? So clustering is not scale invariant. Okay, that's something I forgot to say over there. Okay, but you can see here, right? So in other words, look at you guys, there's two clusters here. Okay, but if I stretch you out along this left to right, maybe there'll be like 5 clusters along this axis alone, right? So clustering is not scale invariant. What you should do is, even though the number have different mean, different standard deviation, you should standardize them. Like for each dimension, subtract mean, divide by standard deviation, for example. Okay, so standardize the data so they are of comparable size. Okay. So let's go back to our example. Let's say these are already normalized somewhere, I think. Okay, so we normalize and find the cluster. Okay, so once I find the cluster, okay, have 1, 2, 3. Now I want to visualize the result. I want to visualize it. Now I have a problem. Can I do what I did just now with the old faithful? I can't, right? Because my data, well, I don't have that many data points, only 400, 200, 400 location. But I have how many dimensions? 12 or 15, whatever. How would I represent that? Anybody? Well, one way is to say, I have 12 dimensions. I just make a plot 2 at a time. Yeah? How many of such plot would there be? It would actually be 12 times 11 divided by 2. That'd be 66 plots. That's too many plots. That's not going to work. You know what's going to work? Radial axis plot. So I can plot 12 dimensions at the time. However, if I plot all the points, it's going to look really messy. So instead of doing that, okay, I'm going to do what? I will not plot the point. I will plot the value for the centroid. Get it? Right? So now I have basically, right, 200 countries, location, I call it 200 countries. Each country has 12 numbers. All right? I can do 200 points, 2 dimensions at a time. That would take me 66 plot. That's no good. So what I want to do is plot 12 dimensions at a time. But if I want to plot 12 dimensions at a time, I have to use something like table plot or radial axis plot. If I use radial axis plot, it's going to look like a cobweb. Can I have 200 cobwebs on top of one another? That's going to look messy, right? So what I'm going to do is I'm going to plot not the individual country, but the centroid or the average for each cluster. So basically all the 12 numbers for the 53 country, I would average them. For the second cluster, I would take number from 118 country, average them. For the third cluster, I'll take the numbers, 12 numbers from 70 country, average them. That would be my centroid. Now I can plot 3 cobweb. That's explanation. So now you will notice that I have this thing called line thickness. I'll show you how that's used later. But there it is. Okay. Now, let me explain. 1, 2, 3, 4, 5. Oh, actually, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sorry, not 12 dimension. 15 dimension of interest. Each the 200 location on Earth separate into 3 groups, 3 clusters. Cluster 1, cluster 2, and cluster 3. You will notice that they don't have the same thickness. You know how I did that? I make thickness proportional to the size of the cluster. So you can guess, you know, without me telling you, there's one biggest cluster that has 118 countries or location. Which one is that? It's got to be the yellow one, right? So these are kind of, but you know, I had to put the label back. So let's put the label. So this is what putting the labels in. So this is the simple code, one line, radial axis plot, data, and then use the line thickness that I calculated earlier, and image size small. So basically one line, but that one line is not going to give you the label. So when you see a lot of line in my code, it's not because, you know, the language is clumsy. It's because I want to specify, you know, names and, you know, notation. So there it is. Case per million, death per million, reproduction rate, total vaccination, vaccination per 100, stringency index, population density, median age, all kind of stuff. So there'll be some kind of green country, yellow country, and blue country. So what is green country, guys? Green country, my guess would be, my green country would be like a very young, maybe Iceland. You know how Pacific Islander, they have a lot of because of the monocrop, they used to have like diverse nutrition, but now their diet's very bad. It's based on canned good and import good and all that stuff. There's like a country like Nauru or something that used to be very exploited, you know, for mining iguana poo for fertilizer or something. So now the whole country has no farmland left, and they have to import stuff. So they only import like high sugar content. So there's a lot of cardiovascular death, maybe heart attack, I don't know. Okay, so there'll be a country that has a high human development index, so this life expectancy. So this country, the green country, has very tough health record, very low life expectancy. Again, everything is scaled from 0 to 1 or something. Okay, because this is normalized. Now, the rest of this is to actually repeat the step above, except I show you what it would like in my line of work when I want to do something like this a lot. So imagine you started out your consultancy business. Your first client is asked you to analyze COVID data. So you do this, okay? Then you realize this way of analyzing dimension and clustering and presenting as a centroid is useful. It's going to be useful for any kind of data analytics. So the section 1.4.2 is about encapsulating the whole thing into like a function. Okay, so this one we can skip. So anytime I have this kind of like a scripty looking thing, I define my own function. So I define the thing that say cluster analyze, cluster and blah blah blah. So I make it into a one line. So when it gets to this point, I can just make one line. That's all. Okay, so that's not that interesting. Now let's start the go back again to the screen. Okay. So far, what have we done? Okay. So far, what have we done? We have done the clustering. Okay. Now I made the case that clustering is basically what you can do with your eyeball if it's 2-dimensional. Okay. So that's it. That's what you want to do. Okay. Now, if you want to do it in 12, 13 dimension, you can do it, but you can't visualize it in the same way. Okay. So what would happen? You have to share the whole screen, I think. Okay. Right. Now, in the example that I show you with the countries, right? I can't make 2 at a time, so I make all the kind of like the clock, right? Clock. And then for each, let's say we make it 8 dimension, okay? 8 dimension. So one country is here, one cluster is here, 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 right? Now you can't see very well, so you make this into a kind of like cobweb. Okay, so that's what. Okay. Eh? And let's say I have another group that's kind of like here, 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 here. Okay, maybe that's a smaller one. Okay, so a big one and small one. By the way, cluster analysis is so useful, you have to definitely be doing it on the exam. So just go back and play with that. Okay, so that's how you would look, right? How would you say? They say this population, we can partition into two groups. There's a big group of red and the notion, the small group of green, but the red one is outstanding here, short here, medium, small, large, and different attributes. Does that make sense? Okay, now, however, I still really want to see this kind of like cluster. Wouldn't it be nice? Wouldn't it be nice if I have something like this? Okay, something like okay, that'd be nice to see, right? That there's a separation you can affirm to yourself. The problem is, what is the axis you put here? You can't put x1, x2, 3, 4, 5. Somehow you have to have artificial dimension. I will call it A1 and A2 that represent 8 dimensions. Does that make sense? Does that make sense? Well, depends on what you mean. Does A1 make any sense? No. Does A2 make any sense? No. But if I can create this plot, would you agree that there's a nice separation? So the whole purpose is to create artificial dimension. That artificial dimension is based on real 8 dimension. Okay? Okay? So the concept here is that somehow you have x1, x15. You have to squeeze it down to, I'm going to call it A1 and A2. Okay? So I can plot. I want to plot, right? Now, remember, if I take 2 at a time, how many combinations? In this case, it's 15 times 14 divided by 2 is equal to 15 times 7 is equal to 105, right? Right? There are, if I'm going to pick 2 at a time, there are 105 plots, right? So I don't want to do that. I don't want to do that. Somehow, I want to do this. This is where linear algebra comes in. If I have a vector that is, what's it, 15? And I multiply by something that is a matrix. Yeah, don't look confused, guys. I'd be really scared. This is matrix multiplication. Then you get something like this, right? Right? This multiplied by this multiplied by this, plus 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 this multiplied by this. Over here. This multiplied by this over here. Okay? Right? This thing, first of all, what does it do? It reduces the dimension from 15 to 2. That's what it does, guys. I mean, you know, don't have to look surprised. It's what it does. So this matrix performs dimensionality reduction. That's it. Done. Now, my question is this is also going to be a huge part of your life. You don't know it yet. You don't know it yet, but this going from whatever here to whatever here is going to be a huge part of your life. This dimensionality reduction is going to be a big part of your life. And I'll tell you slowly why. Okay. First of all, why did I want to do it here? I did it here because I want to plot 2-dimension, right? 2-dimension. Okay. That's sort of like a silly reason, silly request. I just want to plot, so I make it reduce to 2. Okay. That's not the real reason. That's not real reason. Oops. Okay. You guys know about, okay, let's do this. Y is equal to, y estimate is equal to beta 0 plus beta 1, x1 plus beta 2, x2, right? This is called linear regression, right? In what, in how many variable? Two variable, right? Yeah. So this thing, what does it look like? So you have this x1, x2, y, okay? So what you want to do is some kind of data point and you want to build some kind of surface, right? Okay, kind of surface. Now, imagine the surface is a tabletop, okay? And I have this point, 1 point here, 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 okay? This is going to be pretty good, right? It's going to be pretty stable. What I mean is that these are the points that anchor the surface. Now, alternatively, I have this as well, but the point is all kind of lined up. Okay, when you look from the top, okay. So if I have, this is x1, x2, x1, okay, x1, x2, y. Okay, now look at me. 2 situations. One situation is x1 and x2 is kind of spread out evenly. And I have a function of y as a function of x1 and x2. That'd be pretty stable, right? You know, I can plot that. I can create a model. Okay. Now imagine that instead of that, my points are kind of like gathered around here. Okay. Okay. It's 2-dimension. It's 2-dimension. However, it looks like it is highly correlated. Your friend in statistical department would call this a bad problem. Your friend would call this multicollinearity. In other words, x1 and x2 are supposed to be independent of each other, but they happen to be lined up. So when you try to fit the y surface on top of it, it wobbles. If you don't believe me, make a table where instead of having 2 legs spread apart, have the table leg in line. Is that going to be a good table? Yeah, look at this. The reason this table is stable is because 1, 2, 3, 4 is spread out, right? Imagine I'm going to make a table and I have 4 legs, but my 4 legs are here, 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 and here. Do you think that table is stable? No, because it can do this, right? It's a bad model. That is the essence of multicollinearity. What it means is that you think you have 2 variables, x1 and x2. In fact, you don't. You only have variation along that axis. What it means is that out of 2 variable, you only have really 1 dimension. Okay? Really 1 dimension. So if 2 dimension can be squeezed, you can have a situation where the data lines up in 1 dimension. Imagine you have 15 dimension, but real variation can be sort of like in a sub-dimension, like 3. So in other words, finding reduced dimension is not just for plotting. That's the whole point. Finding reduced dimension is not just for plotting. Okay, it's a real problem. It's a real problem. The idea here is that instead of fitting a multi-dimension y is equal to beta 1 x1 and x2, what you should do is what? What should you do in this case? Yeah, exactly. You should draw this line and call it x3, and then y equal to beta plus 0 plus beta 3 x3. That's a good model. Okay? Because there's only 1 dimension. So this 2 is not real. It's artificial. It's just number of random variable. Okay? Number of input variable. But actually, there's only 1 dimension. So this dimensional reduction, first of all, I want you to realize is not just for plotting. Okay? Just now I said I have 15, I want to plot, so I want to reduce from 15 to 2. You can imagine that there's a linear regression equation in 15 variable that should be built on 9 variable. In which case that matrix should be a 9 by 15. Okay? So the first thing, dimensionality reduction is not just for visualization. I have to get that out. That's the most important thing you have. Well, not the most important thing. One of the most important thing to recognize. Dimensionality reduction is not just for plotting. Essentially, you want to have the real variation in the input. That's what it means. Okay? Now, having said that, in the example and for the rest of the book, I show dimensionality reduction precisely for visualization. Okay? So what you want to do is, after you have done the clustering of 200 countries into 3 clusters in 15 dimension, you might want to do this. Compress the 15 dimension down to 2, and then plot it A1, A2, and then you will notice that there's a 118 over here, and there's a 670 over here, and there's a... This would tell you who's close to whom. Okay? Now, let me say that again. That clustering happened in 15 dimension. It didn't happen in 2 dimension. It happened in genuine 15 dimension. I did not reduce to 2 dimension, then do the clustering. That's a bad thing to do. Okay? In fact, there's a heading in the book section that I say, do not do this. And I show example of doing that. Okay? Dimensionality reduction, then clustering. That's a wrong thing to do because you are compressing the dimension first. Okay? So I don't want to do that. Okay? What I want to do is do the clustering in original 15 dimension. Now I visualize in 2 dimension. Right? So these are all countries. These are countries. These are countries. Now, I didn't prepare this picture, but for facial recognition, for object recognition software, a lot of time you will see a plot that looks just like this. Except instead of having the individual plot here as points, there will be actual little icons. Okay? Now, I should have brought that, but you know, it's very ubiquitous. So for example, if the algorithm does it right, you would see a lot of people, say maybe, let's say this is face of people, okay? Face of people. You see a lot of, say, Asian people here, a lot of European people here, a lot of people from Africa, right? Or something like that. I don't know, okay? So there'll be some kind of like natural clustering of facial feature, okay? What do you think that means? That means what the facial recognition algorithm does is reduce dimension for you. Except I can't tell you what is the original dimension of a human face. A human face may exist in some kind of abstract 500 dimension. And when you reduce from 500 dimension down to 2 dimension, these are the Asian, these are the European, whatever. Does that make sense? Does that make sense? In that way, you can imagine that something that pictorial face, human face, can be reduced to vector, right? 2 numbers of vector, right? And this, my friend, is what is going to be with you the rest of your life. It's called vector embedding. Okay, this is way beyond dimensional reduction. Dimensional reduction that is in the book, I have 15 number, I reduce it to 2. What I'm trying to tell you right now is that you can actually have human face in a facial hyperspace, abstract face of human being. You can reduce that down to 2, and you can plot it. Okay, except they don't call it in that case reduction, they call it embedding. Okay, because the idea is you embed it as a vector. Originally, it wasn't even a number. Next, that's what ChatGPT first had to do. It does this from high hyperdimensional space of words into reduced dimensional vector of word. So it is vector embedding of word. Okay, so let me say that again. So let me show you. Okay, so from this is real number 15 down to 2. Okay, this is dimensional reduction, right? Okay, dimensional reduction. Now from 15 down to 9, this is to get rid of multi-collinearity. Okay, this is what statistic people do. Fine. What else? Faces. What else? Word. Now, except word is such a big space. If you compress it to 2, you lose the detail. So I think ChatGPT reduced it to 180 or something like that. Okay. So this cannot be plotted, right? This thing is plottable. This is not plottable. This thing is plottable. This thing is not plottable. So plotting is kind of like, it's not an afterthought, but it's not the only thing you do. So this thing from dimensionality reduction, you go all the way to word embedding. The reason I say that this is going to be the rest of your life is that every single data for the rest of your life, if you want to analyze it with AI, AI can only read vector. So if you are going to work with face, you have to face into vector. Now, technically tensor, but I'm just going to tell you vector right now, but it's called vector embedding, but tensor embedding is it's kind of similar idea. Word become vector. Everything become vector. Molecule become vector. DNA sequence become vector. That's how you have AlphaFold. AlphaFold is a protein folding prediction algorithm from the same team, well, not the same team, but the organization that has the AlphaFold. The reason they could do that was first, they have to embed protein structure into vector or tensor, vector. Okay. Now, I'm telling you that now because it's way beyond data science. It way beyond data analytics. Okay. In this class, it's data analytics, but you need to know this. You need to know this. Now, let's go back to our original problem. Our original problem is I have 128 countries over here. I have 70 countries over here, and I have 58 countries over here. Okay. So the reason they ball up like that nicely is because what? Because this dimensionality reduction is not done randomly. It's done with a purpose. And that purpose is if Thailand, let's say Thailand is close to Indonesia. Okay, with respect to COVID data. If Thailand is close to Indonesia with respect to COVID data, and Thailand and Indonesia are very far from Pacific Island, some Pacific Island country, then this is in 15 number, you will reduce it so that Thailand and Indonesia are close to each other and far from Pacific Samoa, something like that. Okay, so that is the objective function. Remember, everything in machine learning, you have to guide it. You either guide it with true or false. You can guide it with the distance function. You can guide it with this concept. Exactly. The weight in the transformation matrix is adjusted so that Thailand and Indonesia, once multiplied, get close to each other, but far away from this country. So all the red countries multiply by that matrix will get close together. So the essence is not what A1 is. The value means nothing. What matters is that the one that are close in 15 dimension are close in 2 dimension. And that is a powerful concept. This is a representation of objects in a vector space such that the closeness in the real life is represented here. So you can imagine, right? You can imagine what if, forget it, let's all of you, okay? What kind of food you like to eat? People who like to eat similar food will have representation as A1, A2 that are close to each other. People who like different kind of food. So this principle works universally for whatever it is. It's called vector embedding paradigm. Okay. Now, technically, again, sometimes you use tensor, but vector embedding is what you need. There's technical difference between vector and tensor, but for all purpose, it's a vector. So basically things like this, guys. Human being. How do you process information? Brain. Brain is what What does brain take? Electrical signal. So whether or not you use your nose to smell a chemical, you use your hand to take the temperature, you use your tongue to taste the chemical, you use your eye to sense electromagnetic wave, you use your ear to receive air pressure wave. Doesn't matter. At some point, all this gets translated into electrical signal in a neuron. That's why one brain does everything with electrical signal. That electrical signal originates from chemical, thermodynamic, heat, wave pressure, electromagnetic, it doesn't matter. If you want human being to process, you have to be able to detect it. You don't want human being to process ultraviolet. That's why we don't see ultraviolet. You don't want human being to process gamma ray. That's why gamma ray comes, you don't see it. Gamma ray is not embedded in electrical signal neuron. So think about it. All your 5, 6 senses has to be embedded in neural signal space. Now, if you don't have a brain, you have a computer. A computer doesn't care what the input is. Ultimately, you have to turn it into vector or series of numbers. So numbers have to turn to numbers. Colors have to turn to number. Text have to turn to color numbers. Video have to turn into numbers. Sound has to turn to number. Chemical has to turn to number. Protein structure has to turn to number. That's why we are moving toward the world of general AI. Because now everybody, it doesn't matter where you work as a chemist, you want chemistry to translate into numbers that computer can understand. You work with botany, you work with psychology, doesn't matter what it is. Everybody all over the world right now is trying to say, whatever data I'm working with, sound, sight, smell, text, movie, picture, chemistry, everything. If I can only turn that into vectors, there's a hope for me to do machine learning. And that's why this vector embedding is going to be the most important thing in your life. So even though in, say, consultancy work, most of my job will probably take me with supervised learning, a little bit of unsupervised learning. But I'm telling you, this concept of dimensional reduction, which kind of like originate with unsupervised learning, it becomes a more general paradigm for turning everything into computer munchable data. That's why your generation is much different from mine. In my generation, we had advanced neural network, guys. You know, you don't underestimate people of your own. In my generation, we had pretty good neural network. But our neural network did not have the front end that takes anything but numbers. So if I give you a chemical formula, done. If you give it the picture, it doesn't very well. It's the first breakthrough was, and I can give you the order. The first breakthrough was picture. Turn picture into number. That's the job of convolutional neural network. Once you turn that, the next thing you do, you turn word into number. It's called word to vec. It's because you turn word to vec that people can build ChatGPT or transformer. The transformer is built on top of word that has been turned into vector. Okay? Before word to vec algorithm, you cannot have chat transformer. Okay? So the transformer is about looking at series of input. And that series of input turns out to be number representing words. So now everybody say, if you have a series of things, you want to learn this kind of like forward projection generative with a transformer. First thing we do is, what are we working on? Can we turn that into vectors? If we can turn that into vector, we can give it to transformer. So you, in the future, you're going to see not only chat GPT transformer working on language, you're going to see transformer working on, I don't know, protein sequence, transformer working on financial data, transformer working on meteorological data, rainfall, whatnot. Okay? Because transformer is good at looking back and then projecting forward. That's what it does well. Okay? But it couldn't have done that if the words is not turned into vector. So anyway, so that's called dimensionality reduction. Okay. Principally speaking, there you can think of it as two types of dimensional reduction. I'm just, you know, if you don't understand what I'm going to say, that's okay, but I have to say it. So one is to actually reduce the vector into like lower dimension, like 2 dimension. The other one is to do what we did before, which is before you go to lower dimension, you realize that data that's in 1, 2 dimension is actually on a line. And so there's only 1 dimension. This is kind of like projection first, okay? So principal component analysis, you will hear a lot of that. It's one of those. Principal component analysis, it's basically saying you can have data in 500 dimension, but the axis that it varies a lot in, there's only a few. The first one is the first principal component. The second one is the second principal component. So maybe you can have data in 500 dimension, but the variation is only along this principal axis. That's the first principal component. And if you take into that account, maybe there's a variation on the second axis. So you can imagine that, okay, 3 dimension, right? 3 dimension, but the data exists along this imaginary rod that has kind of like a radial symmetry. So you can imagine the first principal component is along the rod. The second is the distance from the rod, let's say. Okay. So that's kind of like projection kind of ish, but you know, don't have to worry about it. The whole point is that dimensional reduction basically compact the space into lower dimension, but you don't do it randomly. You do it for 2 purposes. One, get rid of this multi-collinearity problem. And the other one is, well, you make it so that things that are close in original space get close to the final space. Now, let me give you something that you will never see in any class anywhere the rest of your life. And that's the reason why this closeness matters. You want to know? You want to know why closeness matters? Okay. Now, remember this for the rest of your life. This is your animal space. This is your animal space. Okay? I'm going to compress animal space into 1 dimension. My question is, which one is a better algorithm? Okay? The first algorithm does this. Human. Okay? Human. Okay? Cat, bat, bird. You agree with me, right? Okay? The idea is that somehow human, cat, and bat, they have some kind of closeness in this space. In this case, human is closer to bat, cat than it is closer to bat. And it's closer to bat than it is closer to bird. And bird is closer to bat than it is closer to cat. Right? That's my embedding, vector embedding. In fact, it's scalar embedding because this is one number. Now, compared to this one, where I have human, bat, bird, cat, okay, and chimpanzee. Okay. Would you agree that this one is bad? Okay, I'll tell you why it's bad. Because if I want to build a mathematical model, I can do this. Okay, watch this. I'm going to build a model called SMART. And to fit that data, I can do this. But if I'm going to fit the word SMART, I have to do kind of like human, monkey, and then, the function is going to kind of look like this. So it's not smooth function, it's complicated function. By doing this, I make the model simple. So the better job you do at embedding, the better job you can do over there. And I'm going to show you something else. Ability to fly. Cat and birds are close together. So I can do this as well. See? So by being clever about where I put humans, cat, bats, and birds, I can build simple model that model intelligence, model ability to fly, model size. You see what I mean, right? Whereas if I did this, ability to fly, well, bird is high, and okay, so high here, it's a complicated problem. So in a way, unlike numbers, you have a choice, right? You have a choice of where to put human, bat, cats, and bird. Okay, well, it's the same thing with numbers. You can put 15 dimension into any kind of 2-dimension. I'm going to put it in such a way that closeness is preserved. Okay, sometimes it's called closeness preservation or topology preservation. No, don't worry about it. It's a fancy word. Okay, it preserves the closeness. Closeness matter because if the closeness is intelligently defined, you can build very good model. Because this model is going to be more accurate than that model. Okay? So model is going to be complex. You can't help it. It's going to be complex. But some problems are so hard. Unless you do intelligent embedding to begin with, you can't solve it. So theoretically, you don't have to do the word embedding in an intelligent way. You can do stupid word embedding. For example, you can use embedding that comes from a dictionary, in which case cat and bat are very close together because C and B are close together, right? So use dictionary embedding. That's fine. And then build a gazillion algorithm that will achieve what ChatGPT does. Maybe in 500 years, we could build that model. But that model is so terribly inefficient, so impossible to build. However, because somebody clever figure out that words, human, bat, cats, can be represented as numbers that are close together in context. So the closeness is not about ability to fly, which is just one dimension. It's not about how smart, which is another dimension. It is how close they are in the context of a human language. If cat and bat are close to each other, yes, they'll be close together. Okay? If cat and nastiness are close together, for example, this person is catty, not nice, catty person. They'll be close in the word space too. So it's not just one dimension like ability to fly. This was a dumb example I made up, right? Well, the clever engine is to embed all this so that words that are close together appear closer in, I think, 128 dimension. I'm pretty sure it's 1,000, it's 1,000 maybe. Okay, somebody can look it up. What is the dimension of word embedding used in GPT 3.5? I think it's, what is it? if I don't, yeah, I think it's something like, originally in vector word research, it was the number 300 was the word we used, embed the English language, each word into a 300 dimensional. But I think GPT 3.5 uses. Okay, I think you can ask. Might as well ask. Yeah. So, huh? 12,080 or something, right? There's a number 8 in there somewhere. 1, 2. Oh, so I'm off by a fact. 1, 2, 2, 8, 8. 12,000? Okay, so I'm off by a factor of 10. Sorry, my bad. Okay. Now, here's the deal. Okay. Next week, what I want to do is so far we've been working with tabular data, right? This is data number 1, 2, 3, 4, 5. Again, we don't work with word or text or anything, right? Next week, we'll work with what's called graph data. In other words, the information here, so this is number 1, 2, 3, 4, 5. This is this person's height, this person's education. So everything pertains to this guy. It's called tabular data. Okay, everything pertains to number 2. Everything pertains to number 3. But what if 1, 2, 3, 4, 5? What matters to number 1 is if he's a friend with number 2. In which case, the attribute here is not height, age, whatever. It's whether you know 2, 3, 4, 5. Okay. Now he knows himself. Fine. He knows 2. He knows 4. 2 knows 3. You see what I mean? So the attribute of the item is actually relationship with other items. That's very important. Okay. So how tall are you? How heavy are you? That's your attribute. How tall are you? How heavy are you? That's attribute. You are number 2, you are number 3. But if the attribute of number 2 is number 2 is a friend of number 3, the attribute is an entity. Okay, that data is like a network. In mathematics, it's called graph data. The reason is because this object, 1, 2, 3, is called a vertex. And this is the edge. I know this, and so forth. Right. So this is called graph data. That's next week. Also, the concept, I'm not going to go into it. At some point, as I said before, all this is going to get embedded into a vector. Okay, but that area of research is 5 years from solid. Okay, now it's still working in progress. Unlike things like word into vector is done using that 12,000. Was it 12,288? Are you sure? I thought it was 1,280. Okay. Okay. Sorry. GPT-3. Yeah. Okay. So it's very expensive. Okay. Now, that's not the main focus. The language modeling is not the main focus of data analytics. For data analytics, again, the data that we tend to work with this kind of data. This will be like 90% of your work. This is like a 10% of your work, maybe. I personally am the opposite. I look for this kind of problem. Okay. For example, I'm trying to work with microbiologists. I look at, any of you have taken biology? Okay, well, in biology, you have gene, right? Gene basically tells you what you can become. But gene is like a library. If you don't take out the book, you don't read. Okay, taking out the book from the gene library is called transcription. So it's only when you get the right transcription do you get the right gene expressed. Okay, and that's very important because the gene that makes your eye, the cell that makes your eye also has information about making a foot. Okay, the reason it becomes an eye and not a foot is because it picks up the right volume of the library. Okay, so that's genomic, transcriptomic. That transcription creates protein, proteomic. Protein creates, you know, a bunch of molecules that come together. These are called metabolite. Okay. Now the idea is that metabolite is not created in one go. You need to put this with that to make this, put this with that to make that, put this with that to make this, put this with that to make that. Okay. Now, if I start to draw, this picture, I got this and then this and make that. I got this and make this and make that. And I got this and make that, and then make this and then make that, and then come in with this and that. What does it look like? It looks like a graph, right? So now biologists all over the world are trying to, well, not including what I'm trying to help, put metabolic pathway into graph so that we can do prediction. So we can get AI to have something to say. Okay, so everybody's trying to rush to get everything into vector space, because once you get to vector space, you can throw it to a neural network and do things with it. Okay. So that's my thing. But anyway, you will see why this is kind of a very emergent thing. It's kind of like standalone. That's the chapter 7. This relationship data is the chapter 7. So that is the subject of the class 12, which should be the last class. Because then the focus now is in your project. Again, I told you that I'm trying to work out how I can introduce project early on, but it's very hard because the subject is very dense. But anyway, so next week, what I want you to do is, because chances are you're not going to be working with kind of like graph problem. I will see if I can delay the graph class to later. Does that make sense? Unless any of you want to work in graph like traffic problem or flow, okay? Tell me. If not, what I'm going to try to do is maybe delay the graph coverage to later, or maybe optional, and start to bring your project earlier. So instead of project in the 14 class, it would be like 12 class. If I can do that, that'd be good. I think that's kind of like lesson learned from previous class. A lot of time, you know, student work on a project and there's a lot that can be done to improve, but too late, it's already the last class. So what I want to do is, if possible, and maybe not today because also it's raining, so you might want to go home early. What you want to do is, number one, understand that this class, okay, if we're going to make this like a interactive visualization, probability, modeling, and machine learning. Okay? Doesn't matter what you focus on. You can make this 100% fine, but you better do a good job. You can also make this 100% of your project fine, but you better do like something really cool. This is something that I think you should touch on. There should be some element of machine learning in there, I think, in your project. And doesn't matter, like I told you before, doesn't matter what you do, visualization is gonna be the meat of your matter. So visualization can be the subject of your project, fine. Probabilistic modeling can be the subject of your project, fine. Machine learning is going to be the subject of your project, fine. But I think for this class, I'm going to make it almost mandatory that somehow your visualization has to be up to, you know, you have to present your stuff with, you know, with this manipulate. So this interactive visualization is going to be how you present the final thing. Okay. So obviously, if the interactivity is to change the plot, then there's nothing more to it, right? But if the interactivity is to pick up feature about your dimensionality reduction, your machine learning or something, that would make sense. Okay, so I would really think about either you have a data Okay, something that you want to work with. Okay, the insight should be in the form of, hey, what does my data look like? But I would imagine that this is biggest bang for your buck, basically, right? If you learn how to do this, there's a lot in life that you can play with this. Okay, this alone doesn't. So this would be like characterization there. This would be something that, hey, I want to see if there's a relationship between here and there. And your data can be biology, chemistry, sustainability, something of your own. Okay. Now, here's the homework. Homework is, okay, if this is most of say Basai project-based learning is kind of like a product backward, right? What's your target client? What's the pain point? What's the solution? What can we do with this? What can we do with that? Okay, and that's a little bit pre-formulated. I don't want you to do that. Okay, I don't want you to do that. Same as when I was working for my bank was doing this. My bank said, I have a campaign. I want to design a campaign that would target retail consumer who are going to be using our credit card. So they have this idea in mind what they want to do. And they maybe ask me about what factor is important. And this is how it works, right? You have business model. I want to do this and I don't know how to target. I don't know what factor. I want to do advertising. I don't know if I should advertise on TikTok or advertise on television or advertise on YouTube. Please, data scientists, find me the number. And, presumably somebody in my job would say, oh, I'll look and say, oh, efficiency of TikTok is much higher. So blah, blah, blah. That's how most people think. That's actually not, it works for a lot of things, but to be innovative, it's more like this. You are a bank or you are a company, you have a factory at home, whatever. You work on something. And based on what you work on, you are able to control the flow of information. And from that flow of information, you're smart enough to not let it go to waste. So you have a factory at home, you don't just run it, but you gather efficiency parameter, you gather the rate of defect, you gather the rate of employee turnover, or something like that. So you keep the data becomes something like a wealth, right? If you have that data and that data is better than anybody else can or understand, or in terms of dimension, the data can be better because it's big. You have more it than other people. Chances are that's not it, but you can have more dimensionality, right? Because you have a general population data like how tall are Thai people. But because you work in a garment industry, not only do you have information about how tall are Thai people, you also have, their waist, their ratio between belt size and, all kind of stuff. And that data is richer than anybody else. Okay, not big, doesn't cover the whole world. Maybe your clients, you only have like 1 million suit made. So that's not a lot. Okay, but you have more detail. So think of your data as an asset. That's what I'm trying to say. Think of data asset first. Milk data asset for insight. If you've done it well enough, you can hand it to a business planner to make money out of it. Does that make sense here? You don't have a business idea of doing something and then ask data scientists to estimate something. You as a data scientist, go look at the data, find relationship, find subtle connection, find something, right? Explore it, find something, build model. If I knew this, I can predict that. Somehow this thing is a cluster. Somehow this thing actually is not monolithic. It's a it's a partition of 5 different populations mixed together. Find that. And then think of what kind of business can I build from that insight? That's a little bit harder to do, but I encourage you to do that. And you should do it here, because once you graduate and you work for a company, you are going to go right into the old-fashioned style of working. They're going to have a problem that they conceptualize, and they'll ask you to run the number, basically. Oh, please run the number for me. Okay, that's going to be your junior job. So while you're at Basai, think opposite, think innovatively. Think of getting the insight, milk the insight from the data, and then see if you can innovate some kind of product design, service model, some kind of platform delivery. I don't know, okay? This is very hard because, you know, all you guys from before you get to Basai, you know, we ask you to pitch a project and ask you to, what's your business idea? Your idea comes first, guys. But trust me, I think it can be just as challenging to say, I've got no idea. I'm going to find about reality from the data. Data informs me about what's out there. Then I will be creative from that point. Okay. Now, this is my philosophy. You don't have to buy it, okay? And in fact, you know, you can graduate from Basai, get a job, and just run numbers, and you'll be appreciated if you're a very good number runner. Okay, so you don't have to, you know, subscribe to my thinking. But while in my class, that's what I want you to do. Okay, so I don't know if you have a factory at home, you have a data set you're interested in, you want to learn about biology, you want to learn about cognition. I have some project in mind. Two things I'm working on. One is metabolic pathway. The other one is what's called saccades. You know what saccade is? It's your eye movement. When you look at something, you can follow it, track it, or you can look for something else, you know, you scan things, right? So those are called saccades. I'm trying to use performance of saccades to detect whether or not the brain is going bad. Basically, dementia detection, right? So sometimes if if you're young, you can do this really well. But if your brain is beginning to have some amyloid plaque or something, some problem neurologically, maybe you won't hit the right target, or you go slow or something like that. So that's a data project. That's a data project. Okay, and that comes from the idea that, well, if I can measure saccades, can I get something out of it? Okay, so start from data, and I don't know how to preach that in the thousand time, but you know, I hope you don't forget this. The techniques may change. You get something more advanced. My book in the next edition probably have something else, or maybe delete some of this, add some of that. But the concept of let's milk something out of data, because data is how you get informed about things that is already not told. You know, you read a marketing 101 book and say, old people and young people spend differently. You don't need data to tell you that, right? But you need data to have this kind of very, very nuanced profiling about your client. Well, maybe old but active, or I don't know. Okay, and that can only come from data analytics. So how do we do this? Next week, okay, let's take a vote. Who wants to go to graph theory next week and then go to project later, or who wants to start with the project? Project. I think so too. Let's try that. I would not mind if you miss graph. Well, I would mind because it's really something I like and it's very good. But definitely let's have. So we're going to I don't want you to come up like last time when you say, oh, I want to work on this thing. Okay. I want to say, what did you find out about this thing? So you should have like a data source. You should have some kind of description of the data. It would be nice if you came next week. You say, I went to this data source, Kaggle, GitHub, whatever. And this is what my data looks like. It's got this field. This field is nominal. This is interval. This is ratio. This is this. Okay. It has, I run mathematical fine distribution for all the dimension, and these are the fitted distribution. This is what it looks like. This is how I cluster. Now I want to see if this thing can then be used to, and then we can start talking. Okay, but I want it to start from you guys. Okay, not I want to work on this. And what doesn't excite me. Okay, what about it and how and what you learn about it. And again, start with the visualization, guys. Go back to that. Okay, go back to that visualization chapter and use it. That's it. So okay, so next week we start with that. I'll start maybe everybody come in again, be on time. I'll just randomly you that kind of thing. Okay.